Hello, pre-calc. We're going to have to go on to the next topic. I hope that you made sufficient progress on implicit differentiation. It will pop up in the middle of our new topic, related rates, as will the chain rule. So they're here to stay. So I'm sure you're more comfortable than you were at the beginning. So I'm happy with that. You'll be watching this Thursday after class, and the derivative is going to be front and center today. So, and as you recall, derivative is a slope of a curve at a point where things are always changing. So we're going to look at the derivative as a rate of change. And we have done that a little bit, and we're going to continue on that, build on that. So when things are changing, they are crying out for you to use the derivative. So I'm going to teach two related rates problems today, and the first one is a classic. So you have a ladder, and it is 25 feet long, and it's leaning against a building, and it's given a certain height. I'll call it h, not for hypotenuse, but height. So it's hitting the building there, so the height that the ladder makes with the side of the building is right there. And we'll say the base of the ladder is x away from the wall at ground level. And unfortunately, for the person on the ladder, this is falling. It's going to stay against the wall, and this is going to be coming out. And we happen to know that as this disaster takes place, that the base is moving to the left here at 2 feet per second. And here's the kind of question you'll have to answer. How fast is the top of the ladder moving down the wall? When the base is 7 feet from the wall. So that's the kind of question that we're going to ask. And the question will, when we're doing a related rates problem, the question is always looking for a derivative. So let me give you some derivative symbols that relate to this problem. It turns out that the rate with which h is dropping can be represented, any rate can be represented with a derivative. Anything that is changing can be represented with a derivative. So if we want to know how fast this is changing, we look at dh dt, which is read the change in height with respect to time. You're used to doing something dx, but our variable is going to be time that we are differentiating with respect to. So dh dt, then this spot is moving, and that would be dx dt, the change in x with respect to time. So what we're asked for in this problem is how fast is the top of the ladder moving. So it's coming down like this, dh dt. So we're going to find dh dt. So the first thing you need to do is find what derivative the problem asks for. And since a derivative by nature is always changing, we always need a when. So if there's no when in the problem, you can't do it. But there is a when, so rest assured, when the base, which I called x, equals 7. So to do that, the first step is to find a formula or an equation that relates the variables. Since we're assuming this wall is perpendicular to the ground, we will use the Pythagorean relationship. So that will tell us that x squared plus h squared equals 25 squared. Now you may say, why don't you put in 7? Because this question is asking about the situation when x is 7. But we cannot use x is 7 because that is not constant. It's not always 7. At one moment in time it is 7, but we can't say it's always true. H is not always one value, but 25, the ladder isn't shrinking or growing, it's always 25. So we can put the 25 there. So x squared plus h squared equals 25 squared. And now we're going to differentiate implicitly from left to right. So we get 2x, and then we use the chain rule. Now you're not used to using the chain rule for x, but see, we're differentiating with respect to t. So since x is an expression involving t, we're going to write dx dt using the chain rule for x. Then we go to h, 2h, dh dt, same reason, equals 0. So the derivative of 25 squared. So with that, we should know everything. We should know everything except what we're looking for, and we're looking for dh dt. So let's see if we can fill in everything else. Now that we've taken the derivative, we can put in x equals 7, because this is just a snapshot, one moment in time, and we can put in x equals 7. dx dt, what is the change in x with respect to time? That was also given. It is 2. And we have plus sign, the 2. The height is, at this point, we don't know it, but it can be known because at that moment in time, we've got a 25 going on here, 7 here, so we can get h by using Pythagorean again. So we have 7 squared plus h squared equals 25. So if you solve h doing that, you'll see that it comes out to 24 because 7 squared plus h squared equals 25 squared. And that becomes h equals the square root of 576, which is 24. So I'm going to go back here, and h I have now calculated for this moment in time. It's 24. dh dt is what I'm looking for. And now I just solve for dh dt. So I move 2 times 7 times 2, which is 28, over to the other side, and this is 48. 48 dh dt, 48 dh dt, and I'll move the 2 times 7 times 2, the 28 over here, and divide by 48. And that reduces what? Each by a factor of 4, so we get a minus 7 over 12. So negative 7/12 feet per second were the units in the problem. Does it make sense that it's negative? It does, because this h was dropping, is getting smaller. So, all right. So keep that under your hat, and I'll shut down this part and we'll do one more. But I'd like you to fill in the blanks this time and try to work with me or ahead of me. So see you on problem 2, part 2.